In this video, I want to derive the series expansion of a function that depends on two variables, x and t. This function is equal to capital H, and the function is t plus 2 sine of 5 pi x over L. We will see that the expansion of this function will be an approximation of this function here, and the variables, as I said, are t and x, and there are formulas for the calculation of the Fourier series. In particular, I want to expand it in the following basis: the sine of n pi x over L, with n going from 1 to infinity. And this function is defined in the interval where x belongs to 0, capital L, whereas t is greater than or equal to 0. Now, instead of using the usual integrals for the calculation of the series, which are the following, so we have basically we can expand it like this: h of xt can be written as a summation over n from 1 to infinity. We have the coefficients h sub n of t sine of n pi x over L. So of course we are forced to choose these coefficients to depend on time, because as you can see, this is a function of x, but also it depends on t. So these coefficients would depend on t. Now you can see that such a representation is just an approximation of our function. Why is that? Well, because if you set h of xt, so instead of calculating x and t, so instead of calculating the function at a generic x and at a generic t, we choose x equal to 0, and then we choose a generic t, but you can see that the function gives us t. Whereas in here, if you choose x equal to 0, you will see that this sign would go to 0, and therefore here basically you are summing a bunch of zeros, an infinite amount of them, so we get 0. So why is that? Well, the reason is that the Fourier series is a very good representation of the function, but at the boundary there are some differences between the real function and the approximation. But you can show that in general the approximation is very, very good. And I will not do, as I said, the straightforward calculation. I want to show you in a different manner, which will be more intuitive also to understand why there arise these kind of differences. Also, let me give you the formula for h sub n. H sub n of t can be calculated like this: 2 divided by L, integral from 0 to capital L, h of x and t, sine of n pi x over L dx. So this is just the usual theory for Fourier series. And basically you can, if you want, do these calculations yourselves, and you can find these coefficients to expand the function h of x and t. But here I want to do it in a different manner. In my opinion, it is even more interesting to do so, because as I said, there can be some intuition that you can derive from this, that you can infer from this. Now, in order to do that, let me consider, I want to show you this. I want to show you basically that under a certain approximation, under a certain assumption, a certain approximation, the summation over n from 1 to infinity of sine of pi n x over L divided by n can be set approximately equal to pi over 4. So this is actually an interesting approximation that we will use. And let me tell you why this approximation holds. We will not get into all the mathematical details, but I want to show you an intuitive approach for why this is true and how we can use it to derive the series representation of the function above. Now, in particular, let's rewrite this series. We can write it as summation over n from 1 to infinity sine of pi nx over L. Now we divide n by L, and then we are forced to multiply this by 1 over L. Now, at this point, we can define this pi x in particular. So let me slightly rewrite this in a different manner. We have pi x n, and let me define pi x as some variable omega. So this is just a definition, and then I define n over L as a variable xi. So here we have xi. And what about 1 over L? Well, we can think of 1 over L as, for example, n over L minus n minus 1 over L. So this is just a small difference between xi, and if you want, you can think of this as xi minus a small increment, so minus a small variation of xi, so xi minus the xi. Therefore, this difference will give you the xi. So it's as if we are really performing an integration. So this can be written as approximately. Why is that an approximation? Well, it depends also on how large L is. So we have to assume that L goes to infinity. So L must be large enough, and therefore this series can be properly approximated by means of an integral. So we assume that this is the case. We have an integral from what kind of variable here? From what kind of value? The value is 0, and it goes all the way up to infinity. Why is that? Well, because n starts at 1, so xi, since it is equal to n over L, at n equal to 1 we have 1 over L, and of course, since L goes to infinity, here we must put 0. And then for n going to infinity, well, here we will have infinity. So we assume that n over L, as n goes to infinity, will still be infinity, because L will be large, but I mean, it is very large, but not as large as n when n goes to infinity. So I know that this is just some informal way of explaining that, because you can be mathematically, more mathematically rigorous, but I think that this is quite intuitive for the way in which I want to explain things, at least in this video. So we have really an integral of the sine of omega xi divided by xi d xi. This integral can be performed by means of complex calculus. I will not get into the details of that. So by using the residue theorem, if you want, you can derive the result of this integral. And since omega is greater than 0, and you can see that from here, because x goes from 0 to L, so omega is a non-negative quantity, we get pi over 2. So this is pi over 2, which means that this series here can be approximated by pi over 2, not pi over 4. Now the series can be split in two parts. So approximately the series is equal to pi over 2, because the series is approximately equal to the integral, but we can split the series between the summation over the even integers and the summation over the odd integers. So you can split this into the even integers and into the odd integers. And since L is very large, the difference between these two summations will be small. So approximately this will be 1 over 4 times pi, and this will be approximately 1 over 4 times pi, so pi over 4, whatever. And this is what we are going to use. So in particular, we will use the summation over the odd. So we know that 4 over pi summation over the odd numbers is approximately equal to 1. Now the summation over the odd integers, let me remind you what that is. So we basically have this evaluated at odd integers. So we have the sine of pi x over L plus 1 over 3 the sine of 3 pi x over L plus 1 over 5 the sine of 5 pi x over L plus dot dot dot, and you get the idea, right? So we can use that in here. So in particular, we will multiply t, so this will be approximately equal to t times something which is close to 1, and that amount which is close to 1 is this. So we have 4 over pi, then we have the sine of pi x over L plus 1 over 3, the sine of 3 pi x over L plus 1 over 5, the sine of 5 pi x over L, and then you get the idea, plus 2 the sine of 5 pi x over L, like this. Now you get also the series from here, because the coefficients, for example, the coefficient that multiplies sine of pi x over L is the first coefficient, and we have 4 over pi times t from here, right? Then we have the other coefficients. So this is the basis, but the second coefficient for n equal to 2 would be 0, because we only have the odd numbers, so here we have 0. Then we have 4 over pi t times 1 over 3 for this. Then the fourth term would be 0. Then we would have 4t over pi times 1 over 5. And we also have this term, which gives a contribution, because we have sine of 5 pi x over L. So we have this factor of 2. Then, of course, we have 0. Then we have 4t over pi times 1 over 7, and so on. So you get 0, and you get all the other terms. And this is basically the series expansion that you would also be able to calculate if you use this formula. So you can do this directly. You can see where the approximation comes in. It comes in because we are basically multiplying this t by this function. So you can see that if we set, for example, x equal to 0 here, this term would be 0. So in general, this is an approximation for 1. So it should be almost equal to 1. But for x equal to 0, you can see that this is not equal to 1, because we get 0. So as I said, there is a difference between this approximation and the actual function there. But if x is not equal to 0, then we expect that this will be closer and closer to 1. And we also have to remember that this L should be large enough so that the summation, the series, could be represented, could be approximated by means of an integral.